So I'm going to finish up the climate lecture today in this little video and then move on to soils and species interactions. So where we left off was approximately wind. What causes wind? Why the heck does the wind in Oxford usually come from Indiana? Why does the wind in California, Oregon, and Washington usually come from the Pacific Ocean instead of, I don't know, maybe Las Vegas or Iowa? That's what we're going to talk about. So you can just memorize this. This is good. But we'll also look at a picture to sort of imagine this as well. So first off, surface heating causes air to expand and therefore rise. So any place on the Earth where one area is heating more rapidly than another, you'll get more air rising, more air expanding, and air moving across Earth's surface to fill that void. More dense, cooler air fills that vacuum. And because the entire equator warms, then the air comes from the north or, of course, from the south. So the land surface heats most intensely around the equator. So that air is rising and bringing toward it air from the north and the south. So you combine that north-south motion of the air with the Earth's rotation. This results in what's referred to as the Coriolis effect, and I encourage you to just find your own favorite video online about the Coriolis effect to help you understand this phenomenon. It causes air masses, or in this case wind, to deflect in different directions. This results, the Coriolis effect causes tropical trade winds and westerlies in the temperate zone. So imagine you're standing on the equator and there are these tropical trade winds blowing across the Atlantic and the Pacific and the Indian Oceans. It's as if you're standing in a boat and the boat is floating on the ocean, and the ocean is spinning around really, really fast because the Earth is spinning. And so really what you're doing is you're standing on the surface of this ball that is spinning, and the air above you is standing still. And so as the Earth rotates quickly, it's like you're sticking your head out the car window, right? There isn't a strong wind. It's just the fact that the Earth is moving so quickly. That's essentially the basis of the Coriolis effect. And here we have a picture of that. So we can see these these Hadley cells are huge air masses that occur on each side of the equator. You can see they're like strange looking donuts that go all the way around Earth. And if we look over here on the left, we see that the Earth's surface heats up because of the sun, and we talked about how the sun heats the Earth so unevenly. So it's heating the land surface and the water surface at the equator. That causes air to rise, and as that air rises, it's leaving the surface of the Earth, and it pulls in this denser, cooler air toward it, setting up this conveyor belt of air moving around in this circle in these donuts going all the way around Earth's surface. So the air rises, and as it rises, it expands. That causes the air to cool. It also, of course, gets pushed both in the north and south direction. It gets pushed northward, and as it cools, it begins to fall again, and as it falls, it sets up a chain reaction with this air mass, which is called a Ferris cell. That air mass rotates just like a gear. So the Hadley cell is a big gear, and it entrains this air mass to rotate in the opposite direction. Something similar is happening in the polar air masses as well, where we've got generally very, very cold air masses. So the heating that's coming from these warmer air masses of the Ferris cell, those move northward, and they begin to rise along with air from the polar air masses, and the polar air masses rotate in the opposite direction. And so we have that air motion rising and falling and rising and falling and rising and falling. As this air moves from the north to the south and the earth is spinning underneath it, that sets up the appearance to us that there is now wind coming at us at the equator, when in fact it's just slow air masses moving southward and the earth is spinning underneath it. In contrast, what's happening in the north from 30 degrees north latitude and upward is you have air masses that are already moving at sort of a moderate pace, but then as they move northward, they're moving over a landmass that is rotating more slowly. And so as these air masses move northward across the planet that is moving more slowly, they move across from west to east, and that's why we call them westerlies. And so it's because of this Earth's rotation is we feel these winds blowing at us from the west, and that's why most of the weather in Oxford is coming from the west. In fact, most of the weather across a great deal of the lower 48 states in North America is coming from west to east. So that's how those happen. So what causes hurricanes? This is really important. If we go back, hurricanes that we're familiar with are formed over in the mid-Atlantic region, not down near the equator, just above it somewhat, and they come across and then they rotate up through this region. So hurricanes begin to form out here in the Atlantic, and they come through, and they have a tendency, if they get sufficiently far north, to get caught up in this Coriolis effect and get swirled around in this clockwise direction. And so that's why hurricanes move in that direction in the northern hemisphere. There is a great video explaining what causes the direction of hurricane movement that I want you to look at in the course modules. All right, so what causes precipitation? Think about that. What causes precipitation as snow and rain fall out of the sky, or in some cases oobleck, but that's another story. So what causes precipitation is the same thing that helps cause wind. It is the evaporation of moisture. Water gets heated or transpired out of plants, and as that water vapor rises, it loses energy, and those water molecules that were in gaseous form begin to coalesce. They begin to stick together because they have less energy, and they just kind of stick to each other, form droplets, and fall out of the sky. And so that's why we have a lot of rainfall down at the equatorial regions, because we have so much warm air rising. It has bringing with it lots of moisture that then falls down, and that's what causes rainforests around the equator. Those, what's next? Got it. Those air masses now that are high in the atmosphere above the equator, they are dry, and as they move northward, these dry air masses begin to sink, and as they begin to sink, they're going to be dry, right? So they're going to suck moisture out of the land masses at about 30 degrees north latitude. Not only are they dry to begin with, but they're going to get compressed because as they fall, there's more and more of the atmosphere sitting on top of them, sitting on top of those dry air masses, pressing down. That's what we mean by air pressure. It is literally the pressure of the atmosphere squeezing us. And as that air mass gets squeezed, it heats it up, because that's what happens when you put gases under pressure. They heat up. You condense, you're essentially condensing a certain total amount of kinetic energy in those molecules. Regardless, these air masses sink, these dry air masses sink, they heat up. That makes them even more capable of drying out the surrounding land masses. So you have these hot, dry air masses falling in these persistent high pressure zones, and they suck the moisture out of vast areas of the planet, causing some of the world's great deserts, like the Sahara Desert, the Gobi Desert, our arid deserts in northern Mexico and the southwest U.S. and North America, causing those. Of course, there are other things going on, like as we go into the Caribbean, we have persistent high pressure, but we've got so much moisture as well coming from the Atlantic that we don't have deserts in this area. But certainly in large areas of the world we do, because of this persistent high pressure area. So we've got a persistent low pressure area here with rising air, a persistent high pressure area here with sinking air. And so we get that. We have a little bit of the same phenomenon going on with the persistent low pressure in northern North America, leading to higher levels of precipitation. In fact, leading to a temperate rainforest along this side of North America. The Pacific Northwest, large areas of it are a temperate rainforest. The other thing, in addition to these major air cells and these persistent low and high pressure areas leading to major global patterns of precipitation, another very important one for us is that which is caused by topography. Now imagine that we have, so here's a mountain, which is what we mean by topography, is the shape of the landmass. And we've got our persistent westerlies coming along, moving air. We've got a certain air mass on the left here. It gets pushed, in this case, from left to right. We can think of that as from west to east. And that air mass gets pushed upslope. Well, as it gets pushed upslope, that means there's less pressure on it. That means with less pressure, the air expands, and that expansion causes cooling, and that cooling, as we learned just moments ago, that cooling causes the water vapor in the air to coalesce, those molecules to start to stick together. They form snow crystals and raindrops, and they fall out of the air. And so we tend to get moisture on the windward side of mountain ranges. In lots of area in North America, that is on the western side of mountains. So now we've got this dry air mass coming down the backside of these mountains. Just like before, that air mass sinks again. It becomes squeezed by the atmosphere above it, and it then dries out the backside of these mountains. That's why when you look across the major mountain ranges in the western part of North America, we have very relatively moist western sides of those mountains and relatively dry eastern sides of the mountains, and the eastern sides of those basins, the valleys, on the east side of those mountains. So we have persistent global high and low pressure areas that cause differences in precipitation. We also have what's referred to this as an orographic effect, moving on. That was my sister. So here is a picture from the reading of major mountain ranges. Of course, in the east we have the Appalachian Mountains, which are not quite nearly as heavily or strongly, don't have as strong effect on precipitation as the mountains out west do. This coastal range, this group of relatively small mountains along the west coast, create a serious orographic effect because the water coming from the west into North America is laden with moisture, and it hits these mountains and drops all that moisture into those mountains. And we've got all along this west coast, through Northern California, we have high levels of precipitation, especially in the fall, winter, and spring. The Rocky Mountains also create a similar phenomenon, where the west side of the Rockies tends to be much more moist than the east side of the Rockies. Notably, on the in between those two mountain ranges, in Washington, Oregon, Idaho, Nevada, and Arizona, we have a rain shadow. If we go back, we refer to this dry area on the leeward side or the back side of the mountain. We refer to that as a rain shadow. Just like a sun shadow is a reduction of sun, a rain shadow is a reduction of rain. So we have a great rain shadow in what's referred to as a Great Basin. And even though it's not particularly hot, it's what we refer to as a cold desert, because so little rainfall occurs in this area. We'll get more to that when we talk more about deserts. Those mountains result in these patterns of precipitation that I was just talking about. Here we have a map of precipitation, annual total precipitation in meters. The units here are in meters. This is just from your reading. And so right along the western coast, we have this line, this entire isocline, this precipitation isocline is what we call these lines. An isocline, a line of constant value of 2. Well, that's 2 meters of precipitation falling along that west coast on average, because of the persistent moisture coming from the North Pacific and the effect of that mountain range along that region. That 2 meters is about twice what we get if we come back east to Oxford, where we are. We get about a meter of rainfall, precipitation a year, mostly in the form of rain, but also a little bit of snow. All right. If we move, as long as we're in Ohio, as we move to the southeast, we see precipitation increasing up to about 1.5 meters. So it does get quite moist in that region. If we move north and west, we encounter less and less and less precipitation. And as we move to the far north, we get even less. And certainly in cold areas, the air can hold less moisture, and that's why there's generally less moisture in very cold areas, all else being equal. And this is part of the reason, phenomenon associated with climate change, wherein with increasing average global temperatures, we get, in general, we get more drought because the land is drying out, but also more precipitation and hurricanes because there's more heat and moisture in the atmosphere. Double whammy. All right, climate diagrams. These are throughout the book. And the point of diagrams like this that we see on the left is to understand climate at a glance. And so this is part of our training as informed citizens to be able to read graphs effectively. And climate diagrams, especially as presented in this book, are effective once you get to know the tricks. So they're effective after you get to know the tricks. So the context here, kind of what I see when I look at this graph, is I see the capacity of this area of southern Illinois, its capacity to support plant growth. And that's what all these vertical shaded areas are. That's telling me that this is good for plant growth. So let's walk through the elements of this climate diagram. On the x-axis, we have months of the year. So it starts in January and it goes throughout the year to December. So January through December on the x-axis. There are 2 y-axes, you'll notice, one on the left and one on the right. The one on the left is for precipitation. And you might notice that when you notice that at the top here we've got it says 832 millimeters. This is 832 millimeters. So that's about 8/10 of a meter. So a little less than a yard, or a little less than 3 feet of precipitation each year. This on the top, this is the total precipitation over the course of the entire year. What we see on this axis is going to be the average amount of precipitation that occurs in 1 month. So this is monthly precipitation on the y-axis, and the units are over here in this text. This is also from the reading as well, and these units, these tick marks along the way, this one and this one and this one and this one and this one, these indicate 20 millimeters, and it starts at 0. So this is 20 millimeters and 40 millimeters and 60 millimeters and 80 millimeters and 100 millimeters of precipitation in a month. And as it turns out, this top line is what that precipitation is at this weather station in Chicago, Illinois. Is the average precipitation in those different months. So we see that precipitation is relatively low in January. It climbs throughout the spring and early summer, and then begins to fall in the autumn and in winter again. So we see this generally hump-shaped pattern of precipitation, and this is common throughout much of the central United States. So that's precipitation. On the other axis, we see on the left here, we've got temperature. And what we see on the top here, on the top, that 10.1 degrees Celsius, that is the average temperature across the entire year. So this 10.1 degrees Celsius is the average temperature across the entire year, day, night, the entire year. This is the average temperature. Remember, this 832 is the total precipitation. All right, so temperature. Well, the units of precipitation were 20 millimeters. The units of temperature are in 10 degrees Celsius marks. So we start with, of course, 0 degrees Celsius, which is freezing, 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, and the like. And this bottom line is telling us the average monthly temperature throughout the year. So of course in the winter, the average temperature in Chicago is below freezing. It falls through January, comes back up, reaches a peak in late summer, mid to late summer, and then begins to fall again. So that line is temperature. The top line in this case, in this graph, the top line is precipitation. All right? The fact that we have this, the fact that this water line, this precipitation line, is above the temperature line means that this environment has plenty of water to support robust plant growth. And it's telling us that precisely because of the way it's scaled. So where we have this tick mark on one side, that's 20 millimeters of precipitation. On the opposite side, we've got 10 degrees Celsius of temperature. On the left side, we have 40 millimeters of precipitation in a month, mirrored by 20 degrees Celsius in temperature. So as long as we have this scaling, 20 millimeters, 40 millimeters, 60 millimeters, paired with 10 degrees, 20 degrees, 30 degrees Celsius, that makes these lines, that allows these lines to reflect the relative water availability for plants. And so as a result, with this scaling, as long as you have the precipitation lines above, well above the temperature lines, that's telling me as a plant ecologist, oh, okay, I get this environment. It's going to be, water is rarely going to be a limiting factor for vegetation. Hope that's clear. It's also described in the book. You also might be asking what the heck is up with these black and hatched bars and white space down at the x-axis. These tell us the likelihood of a freezing event in those months. If it's black, it means that on average, at some point during that month, there's going to be a freezing event. Or rather, that the average temperature is below freezing. In these hatched areas, this is telling us, okay, I have to pause.